Okay, good morning, everyone. Hope you're doing well. Not too much to talk about in terms of deliverables. You're all working on Deliverable 8, which is due this coming Monday, November the 2nd. In Deliverable 8, you're going to be putting your KNN on pause for this week and hacking together a database, which, as I mentioned last time, is not the most elegant way to integrate a database into JavaScript, but it's good enough for our purposes in this class. Any questions about Deliverable 8? Okay. My apologies about the video from Tuesday. There was some copyrighted material in there. I fixed that now, so you should have access to the video lecture from last time. Okay, so we are moving slowly into the second last theme of the course, this idea of looking outward, trying to create interactive systems that are interacting more or less directly with the physical world, and they're technologies that are being stitched into the physical world and interacting with it alongside humans. There are lots of different ways we can interpret this outward spread of interactive technology. We looked at one dimension of spread last time, which is social spreading. So creating technology that is used by many people simultaneously, and specifically in the case of crowdsourcing systems, trying to allow people to work together to solve a common problem that would be difficult or impossible for one or a few people to solve on their own. We're going to dive back into Lecture 15 in a moment, which is a different approach to looking outward, which is looking at touch. We've spent a lot of time talking about visual and some discussion about auditory feedback and interaction. If technologies are going to be deployed out into the world, they are able to feel the world and supply feeling, literal feeling on our skin back to us, which is a different branch of human-computer interaction known as tangible computing. So this is the sense in which the thing that we're interacting with is physical in an important way. Of course, your laptop and your cell phone and your desktop are also physical objects, but their physicality has relatively little to do with how you interact with them. In tangible computing, we're paying very close attention to physical forces that are being passed back and forth between the human user and the interactive technology. We'll probably finish 15 today. It's a pretty short lecture, and move on to lecture 16, where we're going to think a little theoretically about this concept of ubiquitous computing. So ubiquity means basically everywhere. So obviously it's a very exciting time for HCI in particular and computer science in general. Our global society is in the process of basically digitizing or computerizing everything on the planet and connecting everything together into one large internet, first of all, and now the Internet of Things. What is the Internet of Things going to look like? What do we want the Internet of Things to look like, and what should it not look like? In lectures 17, 18, and 19, which we'll get to next week, we're going to look at the application of ubiquitous computing in scientific endeavor. So we can also view ubiquitous technology as a new kind of scientific instrument, a new microscope, a new telescope, a new tool that allows us to pose new scientific questions and test those questions using ubiquitous technology in ways that have been difficult or impossible to do before. Okay, the week after that, we will probably start to talk about robots, which are self-moving interactive technologies. They're able to move themselves and literally and figuratively move themselves out into the physical world. Okay, so that's a little bit about where we're going, back to tangible computing, which we started in on last time. We looked at the moving one type of moving pins display, where touch is the sensor modality in which information is being communicated back to the user. Most of the information you get from your devices is visually from a screen or auditorially from ringers and buzzers and so on. So I won't play this video. This was the video that's copyrighted and triggered the copyright infringement in YouTube. But what you saw, if you saw the video last time, you saw some of the ideas about how this application might be used. What are some applications that could be useful where the computer is raising and lowering these pins and constructing 3D patterns like the one that you see here that are changing over time, and a user can either feel those pins or, like you see with the red ball there, place objects and interact with this moving pin display? What might be some interesting applications? If you take this course a couple of years from now and we use the moving pins display rather than the leap motion device, what might you want to program it to do? Give you a minute to think about it, and if you have some ideas, go ahead and type it into chat. Or feel free to unmute yourself and describe your idea verbally. One of the killer apps that the demonstrator showed in the video was allowing their phone to be moved by the moving pins to them when the phone was ringing. I don't know if that's exactly a useful use of this technology, but who knows. This is often true of very new kinds of interactive systems. It's not always clear what the killer app or the usefulness of that technology would be. Any ideas? Okay, think on that. If you have an idea, go ahead and type it into chat, but we will carry on. I'm going to show you another tangible interface now. This is Ultra Haptics. I'm going to play an older video. This was the prototype when this was being developed. This is now being sold as a commercial product. So if you Google Ultra Haptics, you can see a more recent version of this technology, but those more recent videos kind of gloss over the technical details. We're going to watch this video. It's going to go into the technical details of this. And what I want you to do while you're watching this video is to remember our discussion about the actual HCI loop. The output of the user, the movement of the user, becomes input to the interactive technology. It works on that input for a while, and then it provides some output back to the user, which is sensed somehow by the user. If you remember all the way back to the very beginning of the course, we listed all of the quote-unquote input and output devices for a human. What are the various sense organs or sense modalities that humans have available to them? What technologies project onto those various sense modalities? And alternatively, what are the standard input and output devices for computers? But that list of input and output devices is growing, and you're going to see some additions to that list in this video. So one way to do this is to write computer, or write Ultra Haptics and human, and then input and output for both of them, and write that down. Some of these, so what is being projected from the human to the technology, and from the technology back, and in what way, what physical phenomenon is being used?
They allow users to... Interactive surfaces are now common in everyday life. They allow users to walk up and use them with no instruction. However, current methods for providing tactile feedback require the user to cover up the visual content by touching the display or attach devices to their hands. We present Ultra Haptics, a system that provides mid-air haptic feedback and requires no contact with either tools, attachments, or the surface itself. Ultra Haptics uses a phased array of ultrasound transducers to create tactile focal points in mid-air. The array is driven by a stack of 5 driver boards, which receive emission patterns from a PC. The user's hands are tracked by a leap motion controller, and the haptic feedback is projected through an acoustically transparent display directly onto the user's bare hands. There are 4 steps to our unique focusing method. First, we define a large volume around the transducer array, within which we will model the ultrasound field. Then, we position positive control points where we want to form focal points. These tell the system to generate the highest intensity ultrasound possible at these locations. They are then surrounded with null control points. These have the opposite effect, telling the system to generate the lowest intensity ultrasound at these locations. Finally, the phase delay and amplitude are calculated for each transducer in the array to create an acoustic field that matches the control point. This simulation illustrates the acoustic field as we move up from the transducer array. Color represents phase, and brightness represents intensity. At a height of 20 centimeters, a focal point is formed. Above, the ultrasound defocuses once more. Similarly, this simulation shows 5 discrete focal points being formed at the same time. By varying the tactile properties of focal points, such as the frequency, they can be made to feel different from each other. In this scenario, a tactile information layer is created above the display. By moving their hand over the map, the user can feel the population density of a city. The frequency of a focal point represents the density in that area. Here, focal points are created above elements of a music player interface. This allows a user to locate themselves on the interface without looking. Tapping the focal point above the button starts and stops the music. The focal point above the volume slider can be grabbed. At this point, it pulses to inform the user that the system has recognized their grasp. The focal point can then be slid up and down to change the volume. These are just a few of the applications that become possible with the Ultra Haptics system.
Okay, so the idea here is to create this illusion, is to create the illusion of the fact that the user is grasping an object hovering in three-dimensional space over this system. How is that illusion created? So as the name implies, Ultra Haptics, they're making heavy use of ultrasound here. So they have a bunch of these ultrasound emitters, which are built into this base plate. And these ultrasound emitters send pressure waves into the air above them. And by setting the relative phase offset and amplitude of the signals being sent out, as those signals start to move, as those pressure waves move upward from the base plate, those pressure waves interact with one another, and at certain points in space and time above the plate, there are instances of positive interference and negative interference. So these are pressure waves. If you think about actual water waves in the ocean, if you have two waves that are coming together, depending on how they collide with one another, if they're in phase, they're both rocking together. When they collide, they will produce a wave that is much taller than either wave alone. That's positive interference. If the crest of one wave hits the trough of another wave, they cancel each other out, and that's negative interference. So the control points that they mention in this video represent points in space and time when there is positive interference. Waves come together and create a more intense or a higher amplitude wave that is actually felt as vibration on the pads of the fingers, which is not quite the same as the amount of pressure that would be applied to the pad of a finger if you grasp a button, but it's close. For people that have used this device, they report it feels like they're actually grasping some type of physical object in the world. Okay, how is the hand recognized? How is input provided from the human to the device? Exactly, our old friend, the leap motion device. So hand position and orientation is being provided by leap motion, depending on where the hand is. For example, if the hand is in the posture of grasping a knob, and that grasp event is about where the knob should be, they want to give a signal back to the user that they've actually managed to successfully grab this quote-unquote volume knob, even though that knob isn't there. So that information is sent into the ultrasonic array, and the amplitude and phase offset of the transducers are changed a little bit to increase momentarily the positive interference at that point, which from the user's point of view feels like the knob giving a little bit of a vibration. The knob is quote unquote telling the user, I know that I've been grasped by you. Okay, kind of an interesting technology. Again, seems to be somewhat practical. It is on the market at the moment. Okay, so why tangible user interfaces, or TUIs? You know, you're all very familiar with GUIs, which project to the visual sense. Why would we want to manipulate objects and get tactile information back? The largest sense organ that you have is your skin, and your skin gives you huge amounts of information about the world around you, and especially about the objects that you are in physical contact with, right? When you grasp an object, rather than passively looking at it from a distance, you can learn much more about that object than you can just by looking at it. Obviously, if you grasp it with enough force, you can tell whether it's a hard or soft object. What else can you learn about an object through physical manipulation that is difficult or impossible to do just by passively looking at that object? Imagine the ultra haptic system is projecting the illusion of a particular object into space in front of you. The user can't see it, but they can reach into the ultrasonic field and feel and manipulate that object. What might they learn about that object? What might they be able to learn about that object by manipulating it? Most healthy young human infants, if objects are placed nearby, infants will not simply sit there passively and look at those objects. They will reach out and grab those objects. And if you've ever watched a young child interact with objects nearby, you can get a pretty strong sense of what they are trying to learn about that object, right? So obviously petting an object or a pet tells you, as Sarah says, about the material properties of it, or as Matthew mentions, the texture. Difficult to often tell the material or the smoothness or the outward surface of an object just by looking at it. Obviously much better to manipulate it. What else can you learn about an object? This is another instance of how thinking about thinking is misleading. As adults, most of our time is spent passively observing objects at a distance, text, video, listening to your instructor's voice at a distance. But young children are not as visual or auditorially inclined. They learn about their world through touch. Touch provides rich experiences. Shape, obviously, yeah. We are out of practice because we do not physically manipulate objects to learn about them very much anymore. We did when we were young. How else did you learn about physics, the everyday behavior of objects, by physically manipulating them? We can learn whether they're hard, they're soft. We can learn something about their material properties. Shape is another. Dropping them, as Bryce says, is an action. Exactly. What action, what mysteries of objects are revealed by dropping them? What do you learn by dropping an object? Weight? Yep, absolutely. Just grasping it itself tells you something about the weight or the heft. Its fragility, can it be broken or not? How things move based on their material. We can figure out relationships between material, weight, hardness, softness, shape by manipulating them. We often learn there are relationships there. Yep, huge amounts of information to be learned. Whether it separates from other objects. So if I pick up a seeming object, does one piece come away and the other piece stay behind? What is the connectivity of objects? Young children, as they manipulate objects, they are also typically observing their hand and the object they're manipulating. And so they're learning not only relationships between the physical properties through tactile interaction, but also relationships between the visual and the tactile relationships. So something that is separable, if I pick it up, one piece comes with me and the other stays behind. What did it look like before I physically separated it? What are the visual clues that this object is not just a single object, but multiple objects? Okay. We bring our spatial intuitions to bear on objects that we manipulate. For most of us, it is easier to reach out and grab a 3D object than rotate it, compared to using a CAD program and trying to use a mouse to click on various views of an object and rotate it in three-dimensional space. If you Google online 3D drawing program, you can try and play around with this on your own. Very difficult to rotate an object in three-dimensional space to a desired orientation. Be nice if we could use something like the Leap Motion device or the Ultra Haptics to allow people to manipulate or build objects with their quote-unquote bare hands. Okay, for most of us, at least, it's easier to sketch with a pen than it is by painting in a paint application using a mouse. We have years and years of experience of manipulating objects and manipulating them delicately, like a pen or a brush, paintbrush, with our hands, than we do at a distance, so to speak, by grabbing a mouse, clicking a virtual, moving a virtual cursor, and that cursor can grab and rotate and move, and so on. Okay. Here's another example of exploiting the fact that it's easy to manipulate objects, or it's intuitive for us to manipulate objects with our bare hands. This is a project from the Ishii group at MIT, and as the name implies, this technology, the primary object, the focusing object in this technology is literal clay, malleable material. As you watch this video, I want you again to pay attention to what is the feedback loop, which sense organs are being engaged by the interactive technology, and what aspects of our output devices, which in this case is going to be our hands and fingers, are at play here. This is also an example of another branch of HCI known as Computer Supported Cooperative Work, or CSCW, which we've talked about sort of indirectly throughout this course. These are particular technologies that are directed at allowing people to work together. So crowdsourcing is one form of computer-supported cooperative work. GitHub is another one. What happens if there is a particular task where it makes sense for a bunch of people to stand around a common object and collectively manipulate that object, and in the case of illuminating clay, to literally manipulate it and reshape it to demonstrate ideas and brainstorm and so on?
Illuminating clay allows users to simultaneously interact with both physical and computational representations of the landscape. Here we see two collaborators preparing a landscape model to be analyzed with the system. A vivid 900 Minolta laser scanner allows the topography of the model to be captured at a rate of 1 Hz. A Mitsubishi LCD projector casts the results of the landscape analysis back onto the surfaces of the model. The work table comprises of a smooth white surface and a rotating platform onto which a landscape model is placed. We experimented with different types of landscape modeling materials. Plasticine with a ductile fibrous core allows the model to maintain the required topography. The area around the platform is illuminated with a library of analysis functions that can be selected at will. The remaining edges of the work surface are used to project cross-sections of the model terrain. The ScanCast mode projects analysis functions onto the model. These include variables such as slope variation and curvature, shadowing and solar radiation, water flow, and land erosion. The CutCast mode allows users to add surfaces for projection without affecting the simulation results. CADcast allows the user to construct three-dimensional topographical models. This system allows any object from the user's work environment to be used as an input to the system without the need for tagging, tethering, or demarcation. The interface provides a simple means for three-dimensional display where the tangible immediacy of physical models can be combined with the dynamic capabilities of computational simulation.
Okay. What information is being collected by the interactive technology, by the illuminating clay? What is the input to the device or the system in this case? How does the system know to update the visual display that it's sending back? So David mentions a point cloud. So the system is able to know, is able to indirectly infer the local heights of the clay using a point cloud. I think actually they derive a point cloud from the video display, but I could be wrong. Basically, it's getting back curvature of the clay. And then using that, it updates its output, which is a visual output, onto the clay. So this is also an example of multimodal projection. So this system is projecting back onto multiple sense organs, sense modalities for the humans. The humans are seeing changes in visual output, but also feeling changes in the clay, which are either being caused by themselves or by others manipulating the object. Okay, so again, here's a technology. It's a little bit dated at this point. This one did not make it out of the lab into a useful product, but again, it sort of suggests interesting ideas about how to combine visual and tactile feedback. Okay, I think we will move on. Last one, the last tangible computing application we're gonna look at here is the Actuated Workbench. Again, I want you to pay attention to what is the feedback loop, what is the input to the system, what is the output of the system, and what is the input and output from the point of view of the human user.
The Actuated Workbench consists of an 8x8 array of electromagnets. It uses magnetic attraction and repulsion to move magnetic objects two-dimensionally on a flat surface. Here we can see a magnet moving in stepwise Manhattan motion. Here we see an object moving in a smooth circular pattern. Although the array of electromagnets is fixed, the system can create smooth motion by varying the strength of the electromagnetic fields. In addition to magnets, the electromagnetic array can move any small ferromagnetic object, such as a paperclip. Here the user controls the puck's motion with a trackball. Smaller objects can be moved much faster, though their motion is not always so smooth. Magnets of different sizes and shapes behave differently in the system's magnetic fields. This stack of small magnets jumps around whimsically. We use computer vision as a preliminary object tracking technology. Here the user records a path by moving the puck on the surface, and the system then replays that path through magnetic actuation. The blue projection around the puck is a graphical visualization of the strength of each adjacent magnetic field. Here is an example application intended to teach users about physics. The red projected area on the surface represents a zone of attractive force, while the blue area represents repulsive force. The user can feel these forces by lightly holding the puck in different areas of the board. When the user releases the puck, it flies to the red zone of the board, to which it is attracted. Magnetic drawing toys are effective for visualizing the Actuated Workbench's magnetic fields. A magnadoodle allows us to see the fields used to trace the smooth circular path shown at the beginning of this video. The Dapper Dan toy lets us see the magnetic activity in the movements of iron filings on the surface. The Actuated Workbench can be used to control the planchette in a Ouija board game. Like other robust systems, such as the Diamond Touch, presented by Mitsubishi Electric Research Labs in WIS 2001, the Actuated Workbench works even when set on fire.
Okay, I think the grad students who worked on this project went a little overboard with their demos towards the end, but other than communicating with those that have crossed over to the other side with the Ouija board, what might be some applications of this kind of technology? The developers had a few ideas and built them into this video. Assuming you had access to the Actuated Workbench and could program it, what kind of applications might you think about creating here? Remember our discussion from a few minutes back about how it's much more intuitive to grasp and manipulate an object than it is to passively view it from a distance. How might we exploit that fact to make something easier for a user where they can physically manipulate something rather than having to look at something from a distance and learn about it that way? Any ideas? There were several suggestions in this video about creating educational software. So they had an example about trying to teach about electromagnetism, which is an abstract concept for most people, by concretizing it, making the user able to actually feel the pull of a magnetic force as they moved an object across the top of the Actuated Workbench. Most of you have had the experience about trying to learn to play an instrument or learn calligraphy. All of these fine motor tasks that require very careful control over the hand or the manipulation of an object with the hand. The best way to learn this without technology is to observe an accomplished instructor. So call up a YouTube video. Let's say you want to learn Japanese kanji characters. Best thing to do is to call up a YouTube video and watch someone do it. But when you watch someone do it, you have to watch what they're doing, visualize what it would feel like to perform that action, and then carry out that action yourself. So you're going from a tactile interaction, the instructor's tactile interaction with her pen. That's transduced into a video, the visual sense. The student absorbs that visual scene and then has to, again, translate the visual scene back into a motor program, a way to move their hand to reproduce what they saw the instructor do. Imagine instead that you were to grasp a pen that is connected to the actuated workbench, and that pen would pull your hand through the drawing of a kanji character. The instructor might record that using the actuated workbench. So the instructor would grab the object, and the actuated workbench would passively detect the changes in magnetic forces in the magnets underneath the plate, or movement across the plate. And then the system would play that drawing back. I think in this video, actually, you could see an example where someone performed a motion and then the actuated workbench played it back. That could be a potential use for this technology. Difficult to learn something by watching an instructor at a distance. Better to, in a sense, hold the hand of the instructor and allow the instructor's hand to pull your hand through the actions you're trying to learn. Okay, I'm sure you can think up some other potential applications for this technology. We've looked at lots and lots of example HCI systems in this class to date. This one, the actuated workbench, has a particular capability that none of the others have had up to this point. Of course, this system uses magnets. A lot of other systems did not use magnets. That's not the important difference. What is the important difference here? What can the actuated workbench do that none of the other technologies we've looked at so far are able to do? The hint is in the name itself of this technology. No? The actuated workbench is able to actuate or move physical objects in the world. We saw Jibo and Kismet, the Jibo and Kismet robots, which move themselves a little bit, so they are in a strict sense, moving physical objects. This one, however, it's the system that is moving other objects in the world. And if a user grasps that object, both the system and the user can collectively move or manipulate that physical object. Whether or not the actuated workbench ever becomes a useful technology, it demonstrates, again, a potential application area in future HCI systems, which are computer technologies that are able to actually move objects out in the world. And we're going to see much more of that when we come to the robotics section of the course. Bryce says, I work at a bike shop, and the immediate thought for me was a larger scale system that auto-organizes all my tools. And there's a great idea, absolutely, right? So if this workbench were an actual workbench and you're working on something with a lot of metal tools, that might be a great example. Yeah, good catch there. Okay, so again, short lecture today on TUIs, or tangible user interfaces. And again, the idea here is to think carefully about PACT. How would people prefer to carry out an activity? Some activities, it's much easier to manipulate an object and learn something or do something through physical manipulation than it is to passively look at a screen from a distance. Okay, so we're going to move on now to lecture 16, where we're going to think generally about this social enterprise that we are involved in, which is stitching technology into the world. Technologies that can directly sense the world. And as we saw in the case of the actuated workbench, interactive technologies that can literally manipulate the physical world alongside human beings. Okay, so this is my cartoon from the beginning of the course. Priscilla says you could play chess with someone across the world where the pieces move for the other person as you drag them across the board, right? If you love chess or other games, you can obviously play on the computer, but there's something, even in chess, which is a very abstract game, there is something about the tactile element of chess that is often lacking in online games. Okay, so ubiquitous computing. Here's my cartoon history of HCI. Back in the Stone Age, all of about 30 years ago, there were lots of humans, the H's, and a small minority of them had computers. The internet was invented, and these computers started to be connected up. Then the smartphone was developed. Most people in the developing world, if they don't have a laptop, they definitely have a smartphone. There are many, many more smartphones out there now than there are laptops and desktops. The internet continues to grow and spread and become increasingly interconnected. We are seeing the arrival of embedded devices. So these are stationary devices that can sense and send information to devices that are nearby. So an obvious example would be a Wi-Fi projector. We talked about smart light sensors in the Davis Center. So systems that can take input directly from the physical world. They sense things, but they have limited ability to influence the world directly. We're going to talk shortly about robots, which are also embedded devices. They can directly sense the world, but they are also able to move themselves. So this is the world that we're heading towards. How do we make sure that as we continue to architect and build the system, that we think carefully about PACT and we react appropriately when unanticipated consequences arrive, to create this increasingly diverse set of interactive technologies. The world of the future, whatever it's going to be, is going to be not just apps. They're going to be technologies that interact directly and physically with the world, hopefully with humans and not at cross purposes to humans. Okay, that's the idea of ubiquitous computing, putting computation out there in the world. And when it's done right, computers disappear into the fabric of the real world. So one of the most important things about getting ubiquitous computing right is that it should be invisible, right? Or you're not aware of it. Obviously, we're not all together in a classroom, but if we were, I would ask you that hopefully you have your cell phone, but you've forgotten that you have it in your pocket, and hopefully most of the time your attention is focused on the slides and my voice. If your phone is constantly notifying you and vibrating, it is not invisible, it is pulling your attention towards it. As we move around after the pandemic, when we get back to moving around in physical environments, we can see in certain places like Times Square, the technology that's there is not invisible, and that's the point. It's meant to be very visible. But useful ubiquitous technology that is stitched into the world and is there to help you is hopefully most of the time invisible, and you can effortlessly, quote unquote, call it up and use it when you need it, and then when you don't need it anymore, it fades into the background. The most common example that arises in most people's mind when they think about the invisibility of ubiquitous computing is GPS, right? It's there if you need it. You pull out your phone, you plug your phone into your car, and there's a voice that tells you where to go. You don't even need to look at your phone. Your car knows where to go, or your phone knows where to go. It will be quiet. It will not project to your visual sense while you're driving. It will only speak up when needed, and with the press of a button, it disappears. Okay, this is an idea. Ubiquitous computing is an idea that's been around for a long time, dating back to the 1980s, but it's only in the last few years, obviously, that the practical technology has caught up and made ubiquitous computing a reality. There are typically two founders of ubiquitous computing, one in Japan, one here in the US. Ken Sakamura at the University of Tokyo referred to this as computers everywhere. His insight way back in the 1980s, before there were cell phones, is that most people were, and this was right around the time of the beginning of the personal computer revolution, he realized that even in the distant future when everybody had a personal computer, they would still probably only have one. There'd be little need to have two personal computers, and it seems silly for someone to need three personal computers. However, so therefore the number of processors, the number of computers is limited by the human population. However, even back then, Professor Sakamura realized that the number of embedded devices a human uses is only going to be limited by the number of devices they serve. So people in the future may have just one personal computer, but they're going to have lots of other technologies, which was unknown at the time. And those technologies were going to have a CPU inside, and some operating system was going to have to run that CPU. So Professor Sakamura created the real-time operating system nucleus, known as TRON. Why real time? Well, as you've realized now with the Leap Motion device, the software supporting the Leap Motion device is real time software. So the moment that something happens, you can have the system speak up and call a callback function that says, "I have a fresh frame of data." When you're working with embedded devices in the real world, there are events that happen in the real world, and those events are recognized by the operating system and they trigger something to happen, which is different from traditional code where you write a loop and it just does its thing internally regardless of what's going on in the outside world. So that's the idea behind real-time software, and Professor Sakamura realized that embedded devices like cars and refrigerators and airplanes, these were all going to need software that is real-time. In an airplane or a refrigerator or a car, there are events that happen that the software has to deal with immediately. No matter what the software is doing, when that event occurs, you deal with it. So starting in the 1980s, he started to deploy this operating system into devices that were being shipped with processors, and even back in the early 2000s, Windows was being shipped on about 200 million personal computers a year at that time. Already in the 2000s, there were orders of magnitude more devices that were running the Tron operating system running then. So back then in the early 2000s, if you asked somebody what's the most popular operating system out there, at that time most people would say Windows. The Apple was not ascendant at that time, but they were wrong. The most popular operating system at the time was Tron, and that is still true today. So Tron itself no longer exists. It's been folded into a parent company that develops other real-time operating systems. But there are many more instances of real-time operating systems running on the globe at the moment than there are Windows and Linux and Mac operating systems running. Okay. Around the same time, Mark Weiser wrote a research paper called Ubiquitous Computing. So he's the one that actually named this idea of stitching computing into the world. Mark worked at Zero Palo Alto Research Center, or PARC. PARC was sort of the Google of its time. Xerox, the corporation that made Xerox machines or copier machines, had this research branch known as PARC, where researchers were allowed to work on anything that they thought was interesting. It was an amazing place to work back in the 80s. At the bottom of the slide, this is a quote from Mark's paper. Our computers should be like our childhood. So Mark created this important metaphor, which is that, like our childhood, ubiquitous technology should provide an invisible foundation that is quickly forgotten by us, but it's always with us and effortlessly used throughout our lives. Anytime you climb on a bicycle and immediately start riding the bike, your childhood is there with you. What your body learned when you learned to ride a bike. You don't consciously call up remembering how to ride a bike when you hop onto a bike. It's there and you can effortlessly call on it when you need it, and the minute you hop off the bike, it's gone again. Okay. Mark also refers to a book by Philip K. Dick called Ubic. Most of you probably know Do Androids Dream of Electric Sheep, which became made into a movie called Blade Runner. Hollywood has a love affair with Philip K. Dick at the moment. Ubic has not been made into a movie yet, but here's hoping. Over the winter break, I am going to assign Ubic as required reading for all of you that haven't read it yet. Okay. What are some examples of ubiquitous technology that's already out there that has this property? It's invisible and it's quickly forgotten after you stop using it, but it's always there in case you need it. Obviously, most of us are spending much less time walking around in physical environments anymore. But when you do, what are some examples of ubiquitous technology that you can effortlessly interact with without giving it much thought? And then forget it again when you're done. Wi-Fi is the, yep, absolutely. Most common, Wi-Fi and GPS are kind of the most obvious examples these days. What are some ubiquitous technologies that are provided by Wi-Fi, that are supported by Wi-Fi? What are some apps that are particularly useful when you're mobile, when you're out and about and trying to get things done in the world, rather than passively watching and scrolling them on your phone? No? No ideas? Does anybody still play Pokemon Go? The Pokemon characters are out there in the world. They are invisible, but if you bring up your phone, you can locate them quickly and then play the game for a bit and put it back in your pocket. Okay, maybe a bit of a facetious example. GPS and Wi-Fi at the moment are kind of the only examples, but you can start to think about some other technologies you might start to layer on top of cell phones as people move about in their environment. Okay. One of the most important things that is built into most ubiquitous technology, again, is that it is being stitched into the world. It suffuses the physical world rather than sitting as a separate information network within it. The internet is not ubiquitous computing. The internet is ubiquitous. It's available on any computer anywhere in the world, but it is somehow separate from the world, right? It takes some effort to get stuff into the internet. You need to type it in or do whatever you, move a mouse, provide information, or do something to draw it back out again. Wi-Fi and GPS, of course, they are supported by the internet, but those applications are directly interacting with the world. When ubiquitous technology is done right, it should act as scaffolding. Scaffolding is another concept that we're going to draw on from psychology. And as the name of scaffolding implies, humans particularly will spontaneously scaffold the learning of their children, as you can see in this example of learning to walk. Scaffolding should help people learn new skills, obtain information, be aware of new opportunities. Scaffolding is particularly useful when it's difficult for the learner to get started. There's a particular task they'd like to learn or a function they'd like to carry out. They don't quite know how to get started. They need some help. How do you provide that help in the case of a human parent or in the case of ubiquitous technology? And then if it's done right, that scaffolding provides a learning gradient, meaning it provides the learner a place to start, and it suggests baby steps, either literal baby steps or figurative baby steps, on how to make gradual process at that task, how to take small incremental steps to move towards mastery of a skill. As the learner starts to demonstrate increased competency, an accomplished scaffolder will gradually remove the scaffolding to allow the learner to continue on their own 2 feet, literally or figuratively. That's the idea of scaffolding. We mentioned affordances many weeks back, feels like years sometimes. We talked about affordances a few weeks back. These are the two the two foundations of HCI that are brought in from psychology: affordances and scaffolding. We've actually talked about lots of different examples of scaffolding already. We just talked about the actuated workbench, where a student may want to learn kanji. They don't know how to do it yet. They have no idea how to get started. But by grasping an object and allowing the actuated workbench to pull their hand through the motions of drawing kanji characters, that's scaffolding, right? It's giving them a place to start. As I mentioned, the other side of scaffolding is detecting growing competence in the case of the learner and knowing how to remove scaffolding when they signal greater competence. In the case of the actuated workbench, how would you program the bench to gradually remove scaffolding as the user becomes better at signing kanji characters on their own? What is the scaffolding and how would you remove it? Decrease the magnetic field strength, right? Exactly. So in the same way that a parent will grasp their child's hands with less and less force until eventually they let go altogether, the actuated workbench could decrease the magnetic field strength until eventually the user is moving the pen on the workbench by their own and the workbench is completely passive. The other tricky thing for the teacher in this case, or the instructor, is detecting increasing competency. How would the workbench know that the user is getting better at signing kanji on their own? What is the input to the bench? What is the sensory signal? What is the sensory signature that the workbench is looking for to know the user is growing in confidence at drawing kanji characters? How does the system know when the user is starting to stand on their own 2 feet? Remember that in the actuated workbench, there is a camera that can see the position of the pen. And based on the position of the pen, it knows what forces to apply to move the pen. But also the user is moving the pen by themselves. How does the system know the user is getting better at signing kanji? This is one of the trickiest parts of scaffolding. Scaffolding seems intuitive. As the user gets better at something, you gradually remove scaffolding. But thinking about thinking is misleading. It's not immediately obvious how to detect growing learner competency and remove scaffolding. Humans, for very good Darwinian reasons, we are natural teachers. We're instinctive teachers. Even if you've never had a child, if you have a small cousin or a nephew or niece, if you're not a parent, you can still immediately hold a child's hand and sense when they're getting better at walking and know exactly how to apply forces to help that child out. It's something that is inbuilt in us. But in the case of the actuated workbench or any other interactive technology, it is not an instinctual teacher. You need to program that system to know when to gradually remove scaffolding. You're going to have some time to practice this in Deliverable 10, where you are also going to have to detect growing competency on the part of your user who is getting better and better at assigning ASL digits. How do you know? How will you be able to detect, given all you know now about the KNN and the leap motion device, how will you know when the user is getting better at learning what you want them to learn? Okay, I'm not going to answer the leap motion one for you. I'll leave you that one to think about. In the case of the actuated workbench, The workbench, quote unquote, knows the kanji character that is in the process of being signed, is being drawn. So given the current position of the pen, which the workbench can see, the workbench knows what the next position is. The workbench can feel the motion of the user. So there are sensors, the visual sensor can see that the user is trying to push the pen towards where the next point in the kanji character should be. They're trying to move in the right direction, and a tenth of a second later, the magnets actually move the pen to that position. So if the user is pushing and trying to anticipate the movement of the pen, that's the signal that demonstrates growing learner competency. Okay. What are some other examples of scaffolding, either in the physical world? So forget technology for a moment. How do humans scaffold other humans' experiences? Or other examples of interactive technologies that also provide scaffolding? Throughout your lives, your parents and your various teachers and instructors and your friends and family members have either directly or indirectly, or consciously and unconsciously, scaffolded your world, provided opportunities for you to get started on learning something difficult or accomplishing something that would be difficult without scaffolding provided by other humans. Thinking about thinking is misleading. You have been surrounded by scaffolding. For most of you as university students, most of that scaffolding has now been removed. Not all of it, but most of it. What is it? What are some examples of it? We've mentioned bicycles a few times in this lecture. How did you learn to ride a bike? Training wheels, exactly. So two examples are usually given of scaffolding from the real world. The parent-child interaction that you see in the photo here, and training wheels. What are some examples of interactive technologies that provide training wheels to the user and then remove that scaffolding as the user gets better? So a lot of games or complex software, if they detect that you're a new user, they'll provide a pop-up notification or helpful hints or a tutorial. And if you swipe them away, or better yet, you don't have to distract yourself from what you're doing, saccade to the notification, click on it to get rid of it. You demonstrate through your actions that you don't need that particular scaffolding anymore. Okay. I'll leave that for you to think about. Let's think about another potential application for scaffolding that is becoming increasingly urgent. And this is the scaffolding of older people's homes and environments. Ubiquitous technologies tend to appear in indoor environments first rather than outdoor environments. So we're going to focus in this example about trying to think about instrumenting the homes of the elderly to allow them to remain independent for as long as possible. Why is this so urgent? Well, this particular visual design, or this particular figure, shows why. As most of us know, most populations, at least in first world countries, are becoming increasingly older. So back in the 1950, in this particular country, which has not been named yet, in this particular country in 1950, you can see that the majority of the population was middle-aged, but there were many more young people than there were people 65 and older. In 2005, it was about 50-50, well, slightly more people over 65 than under 0 to 14. And the projection for this particular country in 2015 is that there will be, if you sum 35.7 plus 10.8, it's almost greater than those that are working. So in Japan, for example, there are now more people that do not work than work. They do not work because they're retired or they have yet to enter the workforce. How do you keep a country going socially and economically if the majority of people are not eligible to work and the minority are working? This figure is not drawn from Japan. What country is this figure drawn from? And what's the hint that tells you what country this is? It's not the United States. The UK. How did you know that, Ethan? That's correct. Exactly. There's your hint. Okay, not so relevant to our discussion today, but especially during the pandemic era, this is becoming increasingly urgent. How do we keep the elderly, or in some cases the sick and infirm, out of hospitals and health centers and allow them to remain happy and somewhat healthy in their homes? Can we provide technology that is stitched into the home of the elderly or the infirm that supports them and provides scaffolding in their daily lives in their home? Okay, lots of different applications you can think of this. Here's one particular example. We're going to stitch, in some cases literally, pressure sensors into the carpets of Miss X's home. So I'm drawing a graph here with nodes and edges. This graph is drawn according to the URMIA specification. This is entities and relationships. So the entities are obviously the rectangles here. These can be either human stakeholders like Miss X herself, who lives alone in her home, physical objects in her home like carpets distributed throughout her home, telephones, but also sensors and network devices and so on. Relationships are represented by edges connecting objects, and the numbers or variables that are labeled at the tips of the edges represent the one-to-one or one-to-many or many-to-many relationship. So we have one stakeholder, in this case, Miss X, in her home. In her home, she has M carpets throughout her home. For every one carpet, she has N pressure sensors that we're going to stitch into the carpet. I mention URMIA here because for some of you that go work in industry, this is a common notation that's used for creating visual requirements or visual use cases. Remember our discussion early on about design processes for HCI. It's a common notation or a system used for sketching out these kinds of use cases. Okay, so what is the packed analysis here? We are supporting Miss X, but we are also supporting Miss X's caregivers. So this may be Miss X's children who periodically call on the phone, and this could be the phone or the smartphone, doesn't really matter for our purposes, and it rings and rings and rings. If you have an elderly family member, a parent or a grandparent, you probably know this feeling where you call and there's no answer. If you call an elderly person at home and there's no answer, what do you do at that point? There are many explanations for why Miss X did not answer the phone. If you live anywhere nearby, the safest and most humane thing to do is to assume the worst and always hop in the car and drive over. Wouldn't it be nice if there was another way to get a better sense of what's going on in Miss X's home? Imagine that we create these pressure sensors, we hook them up to a sensor network device, which is drawing information from all the pressure sensors and sending an automated text message to the smartphone, which is if I call and there's no answer and I hang up the phone, that call may trigger a text message, which is what's up with Miss X? So, for example, if there is a particular pattern in the pressure sensors, Miss X is up and moving around, a message might be sent saying Miss X is approaching the phone, please wait, or please call back in a moment. She should arrive at the phone in 30 seconds, 2 minutes, 5 minutes. If there are no peeps from the pressure sensors, then perhaps Miss X is not moving around, or at least has not stepped on any of the carpets. She can't hear you, or we haven't detected any movement in the home in response to your phone call. Please send a message to her vibrating pager or drive over or what have you. There's just one example. So obviously this might support the activity of the caregivers for Miss X. It may be acceptable to the caregivers because it provides a little bit more information, but it may not be acceptable to Miss X herself. This is clearly a pretty strong invasion of her privacy and her home. This is a particular aspect of context that arises in health or other support systems for elderly yet independently living individuals. Most elderly individuals are particularly resistant to intrusive technologies and beepers and phones and so on. So navigating the acceptability of health support technologies for the elderly is a particular challenge and growing challenge in HCI. Okay, that concludes our discussion of ubiquitous technology. We're making good progress today. So we've got 4 minutes left, so we'll just start in on lecture 17 now. As promised, we're now going to look at 3 different kinds of ubiquitous technologies, 3 different applications, and these are all scientific applications. So trying to pose a scientific question and test it using ubiquitous technology, where it would be difficult or impossible to test that scientific question without technology being stitched into the world itself. Okay. We're going to start today by looking at ubiquitous computing for learning about social networks. We're going to be focusing on a particular aspect of social networks, which is face-to-face communication. So obviously we can analyze social network data drawn from your favorite social network platform, but what about face-to-face human interactions? What can we learn from a social science point of view about how humans interact face-to-face that's difficult to do without ubiquitous technology? Okay, that's what we're going to look at in lecture 17. So let's just introduce this experiment first. It's quite a few years old now, but this was one of the first attempts to use ubiquitous technology in the social sciences. So some very willing graduate students, 24 graduate students, agreed to carry around sensors which were attached onto the belt of their backpack here. The sensors, as you can see here, is sitting about where their lapel would be, and it's relatively close to their mouth, and it's going to record what they say. Again, you can see this is seemingly a pretty intrusive technology. One of the big acceptability or HCI challenges for ubiquitous computing is privacy issues and intrusiveness. This sensor is going to record the volume of their speech, how loud or how quiet do they speak. And it is also going to record how they speak. This is known as prosody. Do they speak quickly, slowly? Do they speak with clipped tones, or do they slur their speech? Do they have a low or high pitch? So the quality of the speech, but not the content of the speech. The sensors are going to, at the point of the sensor, they're going to extract out actual words and throw them away. So we're going to anonymize what's being said, and this was a nod to the acceptability of this technology. These graduate students have agreed to use this technology for 6 months, but their friends and family members haven't. So even if the graduate students are okay with their words being recorded and used in this study, other stakeholders have not. Okay. The first thing that we're going to look at next time is from this raw speech data, just volume and prosody, the way they speak, can we learn a social network among this group of 24 grad students who are friends and who are not? I think actually let's pause here before we get more. Oh, sorry, last thing I wanted to mention here. Given the fact that we can infer the social network directly from the speech data, is there a relationship? This is the scientific question they're going to tackle. Is there a relationship or a correlation between where you are in this social network and how you behave among this group of 23 other graduate students? Is your face-to-face interaction modified, or is it different corresponding to where you are in this social network? Answering this question would be extremely difficult to do without recording in real time information about how they speak, who they speak to, and so on. I think we'll stop there for today. Remember that you have a quiz due tonight. You're working on Deliverable 8. I wish you a good rest of your day and a good weekend. I have my office hours at 11 a.m. today. Otherwise, have a good weekend. We'll see you back here next Tuesday. Thanks very much, everyone.